There we go. All right. All right. So let's go find out where we are at, with this class. And that's part of, why I have recordings on YouTube is, I also use that to check, what I talked about in the previous class. So today is a Tuesday, so that means the previous class would be 5 days ago.
Today's Wednesday.
Oh, today is, okay, so it's Monday. Yeah, see how I lose track of days. Details. Okay. And this is the live one, but since it's marked, private, so people cannot watch it until I release it. And today is the 11th, so I have to check the one on the 9th. And I just need to know at the very end. So at the very end, we talked about base conversion into base 16. And then shortly before that, we talked about binary addition, how to compute the carry, and also the result in a binary addition. Okay, so very good. So that really helps me to reestablish where I left off. And today's lecture is particularly important to record because on the Tuesday class, I forgot to turn on the recorder, so they missed this part. And I told the class, okay, you can watch the Monday, Wednesday class when I have it today. So in a sense, you guys are their backup. All right, so let's move on to here. And it is important for you to remember, where we are at in terms of the notes, in terms of the reading that you should be doing. We are basically right here at this point. Okay, the next module that we'll be working with is going to be down there a little bit. I think it's binary subtraction. Okay, so right now we are still on binary addition. We are done talking about the R function and also the C function. So let's go ahead and take a look at where we are at this point in terms of binary addition. All right, so this is binary addition, and we just talked about the structure of multi-digit addition. So this part is done also. And this example is using just base 10. And then here we start to transition into base 2. And of course, I'm assuming that we should not have any questions about this part because this is what we talked about on Monday. So is that okay? The only difference between the notation is on when I write something using my stylus, I would use case subscript I+1. But instead of using a subscript, when I write it out in my notes, sometimes I use square bracket instead of a subscript. So that's the notational difference between what you see in my notes versus sometimes what I use when I handwrite something. Is that okay so far? Okay. So now we can move on and talk about implementing a 3-bit by 3-bit adder using just AND or NOT gates in LogicSim. And there's a little bit of instruction, with this exercise. I'm not sure how many people have started to work on this and how many people are interested in looking at the result of this. Because if you guys are still working on it, I don't want to really kind of spoil and tell you what the answer is. But if you have already tried to do this and you want me to disclose the answer, we can do that. So let me know. How many people have started on this one and still is in the process of doing it? Okay, so we got a few people. So maybe I'll talk about this on next Monday. Okay, I'll give you the solution on next Monday. Yes?
I honestly am kind of lost as far as like where to go, what to really do.
Okay. All right, so that's fine. We'll take a look. We'll read out the notes and then I'll give you some clues of how to get started with this. So we'll first talk about what a half adder is, and this section talks about a half adder. So a half adder has 2 input pins, 1 bit one is x and one is y. Okay. It has one output bit, which is the R bit, and it has one output bit, which is the C bit. So the R bit is corresponding to the result of adding bit X to bit Y, and then the C bit is corresponding to the carry of adding X and Y. Is that okay? So you make a component in Logisim that has two input pins and two output pins. One of the output pin is labeled R because it is the result of the addition, and then the other one is labeled C because it's the carry of the addition. That's the half adder. Is that okay? Do we know how to make that component, based on what we have talked about? For the most part, you take the logical expression or the Boolean expression that we talked about on Monday, and you turn it into a circuit using gates. That's how you make this little component. So once you have a half adder as a component, then you make a full adder as a component. So a full adder has 3 input pins. The first two input pins are X and Y, which are corresponding to bits of a number or two numbers that you are given with. The third input is the carry coming from the previous column when you do a multi-digit addition. Is that okay? There are 2 output pins, coming out of a full adder. One output pin is the carry to the next digit. So this C0, this 0 here is actually incorrect. This is actually O, okay, carry out as opposed to carry in. So the carry out as an output pin is the overall carry from one column to the next column, to the more significant column. Now, have we talked about how to compute ki plus 1 based on all the stuff on column k? I think so. I think we did. I think we did talk about it. I'm gonna double check because I might have. So it would be after this, and let's see.
Talking about digit K?
I may not have talked about it, so it's hard. It's difficult. Yeah, I may not have talked about it. So we'll talk about that next, okay? Because that piece of information is important when we are trying to make a full adder, okay? All right, so let's go back to the notes because I do want to make sure that we know how to make a full adder out of this. So we go back to the notes a little bit and okay, let's go ahead and look at the Zerno stuff. Not that. That's a cisp310. But I put my notes, everywhere, so I might have put it like right after this. There we go. Okay, so we may not have talked about this in this class, so it's a good time to start talking about it. This part here is a base 10 addition. Okay, and this is kind of like the abstract version of this. In other words, I look at the 3 digits in base 10, 726, as x2, x1, and x0, and so on. So instead of working with actual digits, I'm now working with variables representing the digits. Is that okay? So x0 to x2 is representing x as a number. y0 to y2 are representing digits of another number. And we want to add x and y and calculate the sum. This row here is representing the partial sum. What do I mean by the partial sum? That's the r. Okay, your r function is giving you the partial sum. 6 plus 5 has a partial sum of 1, but it also has a carry of 1. Is that okay? 2 plus 7 is 9, but 9 plus 1 is a 0 with a carry of 1. So that's how you read the actual concrete example. So when we get to this part here, instead of giving you the concrete values of the partial sum, which is not possible because I don't know exactly what x0 to x2 are and what y0 to y2 are. So instead of giving you exact digits, I just call these digits q0 to q2. So now the question is, how do we define the q's? Q of I is just the result of adding xi and yi. Is that okay? What about the k's? Well, k0 is usually assumed to be 0, but it doesn't have to be assumed to be 0. So sometimes we just call it k0 as an input, other times we look at it just as 0. So that's an exception to the rule. What about k1 and k2? In general, ki plus 1 is the carry of adding xi, yi. So when you look at k1, it can be because of x0, y0. It can also be because of q0, k0. So both of these partial addition can contribute a carry to k1. Is that okay? What about k2? Well, k2 can be because of x1, y1, but it can also be because of q1, k1. Is that okay? So the equation to compute ki plus 1 is to say, well, it can be because of a carry from adding xi, yi, but it can also be because of a carry of adding qi and ki. Both additions can contribute a carry to the next column. Are we doing okay so far with this? Okay. What about sum? The sum bits are the ones that are really important to us because that is the result that we want. Well, the sum bits, once you figure out the k bits or the carry bits, the sum bits turns out to be like super duper easy because that is really just the result. Si is the result of adding qi and ki. When you look at the picture, q0, k0, add these two, you get s0. q1, k1, add them together, the partial sum becomes s1, and so on. So are we okay with this particular picture, especially all the equations that are enclosed in red lines? Yes?
This still works if you get this.
It works in any base. This is just the structure of a multi-digit addition. So it will work in base 2, it will work in base 10, it will work in any base. The only difference when you switch the bases is how R and C are defined. Yep.
Where it says q sub I is equal to r parentheses x I comma y sub I.
Yeah.
You said r is the result. Is that synonymous with partial sum?
Yes.
Okay.
So the result of applying the R function is a partial sum. Yep. Well, I called it a partial sum. Yep. Any other further questions about this slide? Yep.
So we have a circuit for sum and carry.
Mm-hmm.
For
R and C.
R and C.
Mm-hmm.
How do we keep the sum? Like, what is the mechanism? I mean, like, when we have the sum and carry,
Mm-hmm.
and that circuit fires. How do we save that?
How do we
Like,
save?
information that we acquire? Like when we add something,
Mm-hmm.
we put it in memory, correct?
You do not. We do not have the concept of memory until much later.
So when we make that addition, it just goes away immediately. Nothing.
It does not go away. So basically, your output is a function of your input right now. As long as you keep the inputs, like the x and the y's, the same, the output would be the same. But the moment you change one of the bits of your input and out of your input bits, the output bits can potentially be changed right away.
Okay.
Is that okay? So there's no memory whatsoever. In order to look at the result of 101 plus 111, you have to hold the input in that state in order for the output to stay as the result of that addition.
Gotcha.
Yep.
Could you clarify in this lower right box, all the way on the lower right-hand side?
This one?
Yeah.
Okay.
KI.
1. No, this is I plus 1.
Plus
Just my,
one.
yeah, just poor penmanship right here.
Oh, gotcha.
Yeah, so it's Ki plus 1 here. And that has to do with how we end up with this carry. Because this particular carry here is because of 6 plus 5 has a partial sum of 1, but it also has a carry of 1. One way to give you to have a carry of a 1. But this one here is because of the 9 plus 1 here. So that means this addition can give us a carry, but this addition can give us a carry as well. Now, can I know ahead of time without knowing the digits which one is which addition is giving me a carry? I cannot tell. So I can only say that there's a plus here, which is an arithmetic addition to basically say, yeah, it can come from xi plus yi, but it can also come from qi plus ki. Well, the question is, can it be both? Okay, that's a big question. But so far, do we have any questions? At this point, we treat this addition as if it is really just addition and not a disjunction. Yep.
Just so I'm reading the equation right.
Uh-huh.
So the k represents the carryover in that equation, or
The k bits are the carry bits. So k0 is representing the carry bit 0, but because there are no additions to its right-hand side, so we usually assume k0 to be a 0. But if you have fractions, or if you have some other situations where somebody is giving you a carry to work with, then k0 becomes an input. It can be 0 or it can be 1. And then k1 is the carry of bit 1. And in this case, it can be a 1 because x0 plus y0 gives us a carry, but it can also be coming from q0 plus k0. Yeah, go ahead.
The carries are only going to be 1 or 0, right?
Yes. In base 2, for sure. In other bases, I have not done the proof yet, but I suspect so. Any other questions about this slide? Yes?
I'm sorry to go back a little bit. I guess I'm still not clear because we get the inputs, x and y, and then we get outputs r and c. But do we use NAND gates, some combination of NAND gates, to do like a half adder?
Well, we'll deal with that later. So right now we look at this picture, and what you're seeing on the projector right now only has to do with multi-digit addition, or the structure of a multi-digit addition. It does not confine these relationships between q and xiyi, between ki plus 1 and xiyi, qi, ki, and si, the relationship between si, qi, and ki, that is independent of the base that we are dealing with.
Right.
But of course, yes, we are interested in translating everything down to transistors, but we'll focus on just the structure yet first, and then we'll apply these in conjunction with what we talked about on Monday. Then we get the kind of the bigger Boolean expressions. So are we good at this point? Yes? Okay. Okay. So obviously in base 10, the R function is going to be different from the R function in base 2. Is that making any sense? So if you think about, in base 10, if xi is 1 and yi is 1, the R is going to return a 2. Because guess what? 2 is one of the digits that you can use in base 10. Right? But what happens when we're dealing with base 2? If we're dealing with base 2, then the R of 1 and 1 is going to be a 0. Because the quantity of 2 cannot be represented by a single digit in base 2. Is that okay? Same thing applies to C. If you look at C of 1, 1 in base 10, it's going to be a 0. Because 1 plus 1 in base 10 does not give you a carry of 1. And that's because what I said earlier, because in base 10, a digit in base 10 can represent all the way up to the quantity of 9. And 2 is definitely not even close to 9. Okay? But when you look at the carry function in base 2, then the carry of 1 plus 1 is a 1 because the quantity of 2 cannot be represented by a single digit. So you need to rely on the next digit and say, hey, the value I need to represent is too much. How about you take care of a portion of it, and I take care of the leftover. So is that okay? So what I'm going to do now is to extend this particular picture just a little bit. And yep, this is all good. So what I'll do now is I'm going to say in base 2, okay? And this really should not be surprising because this is where we left off from the previous lecture. But I want to represent it here just in a way that is, the notation is more friendly when it comes to typing. But I would use the representation that we used earlier on Monday, and then I'll present what it would look like in engineering terms. I'm not sure whether I talk about it in this class. Did I cover this last time? Okay, that's good. So in base 2, these are all Boolean operations. Okay, ampersand is conjunction, bar is disjunction, and the exclamation point is negation. But we talked about how we can use a shorthand in electrical and also computer engineering. They tend to use a shorthand of multiplication is used to represent conjunction, addition is used to represent disjunction. Okay, that's just a convention in those two particular areas. But I'm going to maintain an exclamation point. I borrowed that from C and C++ to mean negation. Are we doing okay so far with this picture? Okay. And then C is the easy one. Okay, C of xy is just xy, x times y, or x conjunction with y. And we talked about this already. It's because of the truth table. Okay, the carry of x plus y turns out to be exactly the same as the truth table of conjunction. So we go like, okay, we'll just use that. So are we good so far? Yeah? Okay. So when you combine all of this stuff here, okay, I hope I have enough space. So now you can express qi over here. Use this way of defining R, and you can just say that, so qi is not xi, yi, the whole thing, or xi and not yi. I mean, I'm just reapplying, this equation over here. Does that make sense? So this means, now we can really express multi-digit addition in base 2 only using Boolean operators. Are all the pieces connected at this point? So let me just kind of explain that one more time. The red lines, okay, all the equations in red line, they basically describe the structure of a multi-digit addition regardless of the base. Okay? And if you're talking about base 10, no, you cannot use transistors to do that, okay? Because, well, at least not easily. But when we talk about base 2, then the R function becomes this, which is a Boolean expression. The C function becomes this, which is also a Boolean expression. So when we combine base 2, which translates everything into Boolean expressions, with the structure of multi-digit addition, now we can come up with the circuitry to perform multi-digit addition in base 2. Yep.
So I originally had this question with base 10, but it seems to be if we're end up having to carry out on the last digit and you end up needing an extra digit than what you started with. What happens if you need to plan ahead and add more transistors do you need?
Okay, so that's a good question. So let me see if this is going to answer that question. The question is, what happens to the last carry, basically, right? Okay, so let's take a look at the structure of 3-bit by 3-bit addition. So once again, we got x2, x1, x0. y2, y1, y0. And I am going to not represent anything, that is not important here. So we got k0, k1, k2, and then we got some s0, s1, s2. But we also have a k3. Okay? So the result, let me highlight which portion would be the input to a 3-bit by 3-bit adder. The inputs would be these bits, all the x and all the y's, and then k0 is also an input bit. Okay? I know it looks kind of strange. It's like, how come k0 is an input instead of a constant of 0? Well, to make it flexible. Because once it becomes an input bit, you can always connect an input pin to a 0. No problem. But if you turn it into a constant of 0 internally, then you cannot turn it into a 1 anymore. So just to remain flexible, we'll just look at k0 as, we'll make it an input bit. Okay? And I'm going to use green to highlight the output bits. Most of the k's, we don't care. All of the q's, we do not care. But obviously, the sum bits are important, right? I mean, after all, this is an addition. And if we throw away the sum, then why do we go through all this motion to begin with? Doesn't make sense. So obviously, the sum bits are definitely the useful output. And you might notice that, but what if k3 is a 1? Don't we need a s3 too? The answer is no. Okay, when we deal with binary addition in the context of a processor, the width of the input is going to be the same as the output. So if we are dealing with 3-bit numbers as input, then we only deal with 3 bits as the output, which is the sum. The output cannot be wider than the input. Is that okay? Then what about k3? Because k3 can be a 1 or a 0. Well, guess what? k3 becomes its own output. But it is not considered a part of the sum. It is just a bit hanging out on its own, to indicate, do we have an overall carry from this addition? But it is not considered a part of the sum. Is that okay? So once again, red line is input and green line is the output. So I'll double make sure that we understand which part is which part. Is that okay? So the ungraded assignment is asking you to make a half adder first, and then from a half adder we make a full adder. So the full adder, when you think about the responsibility of what is a half adder versus what is a full adder, okay? So a half adder has 2 applications in this case. So when you use xi, yi, okay, xi plus yi, a half adder would give you this. Okay, I'm going to keep the same color scheme here. So the output of the half adder will give you the qi, right? That's the r part of the half adder. But it will also give you one part of the carry of ki plus 1. Okay, so I'm just going to not name that thing for now. And then you have another half adder. So the other half adder is a little bit more confusing because the input of the other half adder is qi. So qi is one part of the input of the second half adder, and then ki is the other input of the other half adder. So when you look at qi as a half adder, ki as a half adder, the r output of this, which will appear in green because it's an output, becomes si. Okay, that's pretty clear because we know how si relates to qi and ki. It is really just the result of adding those 2 bits, the partial sum of those 2 bits. So now the biggest question is, what about ki plus 1? So ki plus 1 in this context is in green because it is the output of the full adder. But now the question is, how do we calculate it? Remember, each half adder has a carry output, and we have not designated how to use that particular output from each half adder at this point. Okay, let me say that one more time. Xi plus yi has a carry. It is one of the outputs of the first half adder. But right now that half adder, the output, is just dangling, no one is using it. The second half adder, which takes the output of R from the first half adder, which we know as Qi, and it will add it to Ki, which is the input from the previous full adder, and it will give us Si as the R because that's the partial sum of these two terms. But once again, when we add Qi and Ki, it also has its own carry output, and we are not using that carry just yet. So what about this Ki plus 1? We already know that Ki plus 1 is the carry of Xiyi, okay, which is a pin from the first half adder. And at this point, we'll say this is the sum. Okay, this is not disjunction; it is a sum, and we want to add it to the carry of Qi Ki. Is that okay? We have seen this equation already. Okay, so it should make sense. Well, but guess what? This is the C pin, or one of the outputs of the first half adder. This is the output of the second half adder. So the output of a full adder, the K, or the carry out of the full adder, is really the sum of the carry of one of the two half adders that are inside the full adder. Now, I can draw a picture, but if I draw a picture, that will give you the solution of the whole thing already. So I want those of you who are still working on it to have a chance to work on it. And that's why I'm not drawing the picture yet. Okay? So I'm trying to describe the relationships between the pins, but without using a picture. Then that's kind of hard. Is that okay? But I have a question here. If this plus here, if this addition symbol is representing arithmetic addition, don't we have a problem? Because we want everything to be implemented in logic gates. Is that okay? So we have a question. Can we change this addition into a real OR? Okay. So let's expand the equation here. What is C of Xiyi? Well, it really is just Xiyi because it is Xi and Yi, and in the computer or electrical engineering notation, we use multiplication to represent it. Not a problem. So that also applies to Qi Ki, okay? Because Qi Ki, the carry of Qi Ki added together is really just Qi and Ki, because if both are ones, then we have a carry of 1. So now the question is, given this, is that really the same thing? And I put a question mark here because we are asking that question. Is it really the same thing as using a OR in place of the addition? So the first line, the plus, really means addition, as in arithmetic addition. The second one uses, I emphasize that this is a logical OR. What is the difference between addition and logical OR? Well, let's think about the 4 cases, right? Because Xi, Yi is Boolean, so is Qi, Ki. So now we are dealing with just zeros and ones on both sides of the operators. Yes? They will not give us the same answer. Okay, very good. Okay, so we have the answer already. If both sides are zeros, we don't have a problem. 0 or 0 is the same thing as 0 plus 0 because the result is just 0. 0 plus 1 is 1. 0 or 1 is also 1. Not a problem. 1 or 0 is 1. 1 plus 0 is also 1. Not a problem. 1 or 1 is 1. 1 plus 1 is 2. So we might have a problem. So now the question is, can that happen? Can Xiyi be a 1 and at the same time Qi Ki is also a 1? Can that happen? You cannot think of a scenario, but can you prove that that scenario cannot happen? It cannot happen. And why can't it happen? What is Qi? How is Qi defined? So let me write it out because it's more difficult to verbally describe it than to look at the equation. So let's take a look at Qi. Qi is defined to be the result of adding xi, yi. This is coming from the structure of a multi-digit addition. Okay, it's kind of like by definition. But when we are dealing with base 2 numbers, how do we translate that? It becomes the negation of xi and yi, or, okay, I'll emphasize this is just or, xi and not yi. Remember that? So let me ask you this question. If I know that xi, yi is a 1, doesn't that guarantee that xi is a 1 and yi is a 1? Because with a conjunction, the only time a conjunction will give you a 1 is when both sides of the operator are 1s. Is that okay? So if I say xi, yi is 1, it means I also know that xi is a 1 and yi is also a 1. Right? How would that impact qi? Qi has to be 0. If xi is a 1 and yi is a 1, then qi is guaranteed to be a 0. Oh, that is good for us. Because that means if xi, yi is a 1, qi has to be a 0. I don't even need to care whether ki is a 1 or a 0, because if qi is guaranteed a 0, then the conjunction of qi and ki is guaranteed a 0 as well. So that means in this limited context, whether you use an arithmetic addition or a logical or, either will work. But that's good, because if I can use a logical or in place of an arithmetic addition, that means I can implement that using logic as well, using a logic gate as well. This is how you combine the C pin of the first half adder and the C pin of the second half adder to become the actual carry out of the full adder. Is that okay? So hopefully with this discussion, after some digestion, you will be able to make a 3x3 adder using only half adders and full adders. Okay, I can give you the answer on Monday, but I don't want to give it today because I want you guys to have a little bit of time to think about it. Okay, maybe over the weekend. Is that okay? So this is kind of an informal, assignment to you to work on. Just spend some time to work on it, to try to figure it out. If you absolutely cannot, it's okay. I will give you the solution on Monday. But by thinking about it, it will help you understand the material. Is that okay? So that is, so that basically marks the end of the discussion of a carried ripple adder, which is 5.1 in the notes. So now we're going to move on to section 6, which is, but wait, there's more. And I think I might have mentioned, see, the problem with teaching 2 sections of the same class is I cannot remember what I said in each class. I might have said it in the other class, but then I get confused. There should be a little word here that says way. It's not just more, it's way more. But I will try to describe the whole thing in small steps, okay? Without spoiling without disclosing the answer to the entire full adder thing, I'll tell you what it looks like, just in general. There'll be something from one full adder that has to go into the input of the second full adder, something from the second full adder that has to go to the input of the third adder, and so on, okay? Like that, okay? Now, obviously, this is not the entire circuit of an adder. I'm just focusing on one part of it that expresses a dependency, okay? In order to calculate bit k, you have to know one of the results of the previous column, k minus 1. In order to calculate k minus 1, bit k minus 1, you have to finish the calculation of k minus 2, and so on, all the way back to k0, bit 0, okay? So that is not a good thing, because that means if you know how much time it takes to add two 32-bit numbers, and you want to implement an adder for 64-bit number, you know that it will take twice as long. So a 64-bit adder will take twice as long as a 32-bit adder. Why is that bad? Yep.
It's a linear time complexity, so the bigger.
The more bits you're adding, the more time it's going to take.
Right,
So inherently, it is not quote unquote a bad thing. It's a bad thing only if your competitor has a faster way to do it. So let's just say that Intel says, oh, this is very clean. It uses a very small number of transistors. We'll do it this way. Okay? And then AMD comes back and go like, guess what? We found a faster way to do addition that is not linear to the number of bits that we are adding. So what do you think Intel has to do? They have to retaliate, yes. So they can spend the money on a few things. Okay, so you guys can tell me which way would be the best way to spend their money. One, they spend the money on lawyers. Find something, okay, come up with something and say, AMD, you just infringed on 317 of our patents. Deal with it. I'll see you in court. Unless you stop using that faster way of doing addition. Then we'll drop all the lawsuits. That's one way to do it. Now, I'm not saying that Intel did that or any tech company did something similar to this. I'm just saying that it is one alternative. Two, they spend the money on commercials. We'll re-invite those blue men. Remember the blue man doing all the drum stuff. We'll re-invite those people and drum up, no pun intended, business for Intel processors. People will buy Intel processors because it looks cool, because of the blue man. Okay, so that's the second way to spend the money. The third way to spend the money is to hire more engineers or more qualified engineers and go like, guys, how did AMD get that done? I think we need to do the same thing. We need to stay competitive. So assuming that Intel is going to go for the third option, how do we improve an adder? How do we remove this dependency of between the bits? That is, yep.
You do it in parallel?
You have to do certain things in parallel. Very good. Okay, so the key is to do something in parallel. But we have a problem. So we apparently have a problem with that. Because when you look at the equations of ki plus 1, okay, now I will explain this later on, but if you just kind of bear with me and focus on the first and the last lines, okay, I cannot display both at the same time. To shrink it one more time. There we go. So forget about everything in between. Just look at the first and the last line. There is still a dependency, doesn't it? Ki plus 1 still depends on ki. And then ki depends on ki minus 1, ki minus 1, ki minus 1 depends on ki minus 2, and so on. Okay, so it seems like inherently, because of the structure of a multi-digit addition, there's always that dependency. Is that okay? So apparently we have a problem that cannot be solved. So how is AMD doing it? Yep.
Did they break up the number?
No, they did not break up anything. What they did was this. Okay, so the first thing they did was to say, it's a notational change. Now this is not actually what AMD did. It's just, that's fictional, right? So the first thing we do is we come up with a new term called GI, okay? G of I. And we define G of I to be the conjunction of Xi, Yi. Okay? I'll explain why we use the letter G later, but for now, it's just a definition. G of I is, by definition, Xi and Yi. Is that okay? It's just a definition. And we also define P of I. So P of I is defined to be X of I or Y of I. So this addition symbol means disjunction. It does not mean arithmetic addition. It means disjunction. But nonetheless, we are just defining two additional terms. One is GI, one is PI. Big deal, right? But you can see that, oh, I can see where we can use GI. This is GI, right? And I can also see where we can use P of I, which is right here. Yeah. So without a lot of, trouble, we can now redefine, K of I plus 1 to be G of I plus P of I and K of I. Are we doing okay so far with this? Yes? Have we removed the dependency between K of I plus 1 and K of I? Nope. But we have changed the notation. It looks a little nicer now. Yes? Okay? So, okay, it's still not working. So what do? So what we do now is we just work it out. Okay? So K0 is given, so we don't have an equation for K0. K1 is the first one. So when you plug in I being 0, and you expand the equation, this is what you get, right? Are we doing okay so far with this? So, okay, this is no big surprise. K1 does depend on K0. Okay. Next, we work with K2. So when you work with K2, the first line of the derivation, which is this line here, is really just based on this, isn't it? In other words, instead of using Ki plus 1, I say, what if I is 1? Well, if I is 1, then we end up with this equation here, the first line, which is K2 equals to G1 plus P1 K1. Are we doing okay so far with that expansion? Then you will say, but we still need to depend on K1. K2 depends on K1. But we know what K1 is. This is K1. So what we do is we substitute. We take this K1 out, and then in place of K1, we plug in what we have already expanded K1 to be. Is that okay?
So it's like recursion almost?
In a way, yes. In a way, it is kind of recursive. So once I'm focusing on the second line right here. You can see on the second line, there is no dependency on K1 anymore. K2 is now directly depending on K0 without any dependency on K1. K1 is no longer mentioned. Okay? Now I will take it one more step. I'm going to use the distributive law in Boolean algebra and multiply P1 to both terms inside the addition. And yes, you can do that in Boolean algebra as well as in normal algebra. Yep.
Can you multiply that? That just says P1 and G of 0.
Yes.
Right?
Yep.
Just to make sure.
Yep. But so conjunction works kind of like multiplication in Boolean algebra, and then disjunction works kind of like addition in normal algebra. So there are many laws, many axioms that we use in algebra that can be carried over to Boolean algebra. So is that okay? With this part here, do you see how K2, when we express the whole thing, only relies on the G terms, the P terms, and K0, but it does not refer to K1 anymore. We don't have a dependency on K1, just K0. Okay? But then you guys will say, but there's a whole bunch of extra terms now. There's a whole bunch of G1, G0, P1, P0, and so on. Well, what are those? How are those terms defined? G of I is X of I and Y of I. They can be done just like that. Okay? Next question. Can it be done in parallel? In other words, I look at all of these terms and say, how many of these terms can I compute in parallel with the other terms, meaning occurring at the same time? Can I come up with G1 and G0 at exactly the same time? They can be done at exactly the same time because G1 only depends on, guess what? X1, Y1. G0 only depends on X0, Y0. So those two conjunctions can be done at exactly the same time. I can get to the results G1 and G0 at exactly the same time. While I'm working on the G terms, can I work on the P terms in parallel? Yes. Absolutely. because P0 is X0 or Y0. There's no reason why I cannot compute an AND and an OR of the same inputs at the same time. So this means I just need a very small amount of time to come up with all the P and all the G terms. K0 itself is an input. It is always there. There's no computation involved. Once I have all the P and the G terms, then yes, I have to combine P1 and G1. This will take a second stage of gate to do it. And then P1, P0, K0, that conjunction will take a second level of gate as well. Okay? And then there's one last level of gate to do the final OR, to OR all the terms together. Yes, so we do need some additional stages, but the key is there's no dependency of K1 on there's no dependency of K2 on K1 anymore. We have broken that dependency. So the next question now is, well, that looks kind of cool. What about K3? What does K3 look like? The derivation is almost the same, it's just a little bit longer. This is how we look at K3. The first thing is to use the general equation, and this time we look at I as 2. Okay, so imagine I has a value of 2, so Ki plus 1 is G of I plus P of I times K of I. Okay, so we have a dependency here. K3 depends on K2. But guess what? We know how to express K2 only using the P terms, the G terms, and also K0. So we use this definition, the last line of defining K2, in place of K2 here. Is that okay? Do you see how useful that trick is? Once we know what K2 is, we use the definition of K2 in place of K2. So therefore, we remove the dependency on the term K2. Okay? So after we multiply out everything, we get this term here. And again, all the P terms and all the G terms, they can all be computed at the same time. They're all parallel. Doesn't take a whole lot of time. Right? What about the second level of gates? Well, we need second level gate of conjunction here, and a bigger conjunction here. That's the second level of gates. We also need a third level gate to do all the ORs. Okay, take this, take this, take this, take this, feed it all into one single OR gate, and then the output becomes K3. So let me ask you this question. Now that you can see how K2 expands and how K3 expands, regardless of how many transistors are needed, how does one take more time than the other? Okay, so somebody said yes. So which one is going to take more time? Say that one more time.
I might be misunderstanding the question.
Okay, so the question is, in the calculations of K2 and K3, does one take more time than the other? You have an infinite number of gates to use, and you can wire up the gates any way you want. Okay, does one take more time than the other? Exactly, they take the same amount of time. Well, one is more complex. If you look at K3 and you build a circuit to do to compute K3, yes, it will look messier. It will involve more gates. But the question is, does it take more time? And the answer is no. It does not take any more time. It just looks more complex. Because once again, the bottom level of gates, those are the ones doing all the G1s and all the GIs and the PIs. Okay, we just have conjunctions and disjunction gates to do all that. Okay, once we have the G's and the P terms, then the second level of gates will be doing the conjunctions, P1 and G0 in this case, P1 and P0 and K0 in this case, and in here we just have 3 conjunction gates. Yes, it is more, but they can all be doing the computations at the same time. After the second level of gates, which are all conjunction gates, we have the last level of gates, which is a big disjunction. We take these, feed it all into one disjunction, and that's the output K2. We take all of these, feed all of them into a bigger disjunction gate, and the output becomes K3. So the bottom line is we have removed the dependency between Ki plus 1 and K of I. Okay, there's no dependency anymore. And not only that, the amount of time in theory to compute K of whatever is identical. You can be computing K64 of a 64-bit adder. It will take, in theory, the same amount of time as it takes for K2. It does look a lot more complex. You will have like 60-something terms in the last disjunction, and then each conjunction term is also going to be quite complex depending on which one you're talking about. But in terms of how many levels of gates you need, it is still 3 levels. Is that okay? So this is why this method or this technique is called carry look ahead, which is a misnomer. We are not really looking anything ahead. All we are doing is we are computing the previous carry using an expression, and therefore can expand that expression and therefore remove the dependency of K3 on K2 or Ki plus 1 on Ki in general. Is that okay? Okay, so let's go back and look at the pi needles, okay? The pi needles is Boolean algebra, okay? What makes this possible? Okay, there's the distributive law in Boolean algebra, and then earlier, we have this really, huge long derivation, which I will explain in a moment. So we got a lot of pi needles, okay, based on Boolean algebra and based on the structure of a multi-digit addition, and also based on, how we can define the result and the carry of Boolean addition. Those are pi needles. Are they important? Yes, but we also have to focus on the tree, okay? So if these are all the pi needles, what is the pine tree? The pine tree is basically saying, well, we have different ways of doing addition. The earlier way, the one that you're supposed to do in the ungraded assignment, is called carry ripple, because the carry, if you look at how it propagates, it is rippling through the full adders, and that's why it's called a carry ripple adder. This is called the carry look ahead, which does not have the dependency between the carry bits, and therefore it can be done a lot faster compared to carry ripple, especially when you're dealing with like 64-bit adders. So that's the pine tree.